Hello, everyone. Welcome. How are you? I hope you're doing well. Hope you had a good little break, and welcome back. Um, by the way, uh, I looked at all the exam results, and they were fantastic. So you guys did a really good job on the exam. Most of you got an A, a B, or a C, and a few of you didn't quite get there. And if you're in that boat, then that just means you're not keeping up with the class, and you probably have to um, be a little more diligent about staying with the assignments and doing the work. If you want to brainstorm with me about how you can do better on the next exam, feel free to send me an email, and we can chat about it. We can set up a Zoom meeting, and we can meet. So I'd be happy to do that. Okay. Um, let's see. Before we get started, we're going to start talking about equilibria today, and we're going to spend quite a bit of time on this topic. So just before I start, are there any questions?
Got a quick question about the pre-lab lecture. I don't see it on the home page under the pre-lab lecture recordings. Other people are saying that it's posted and it's.
I think it's date. It doesn't have the date for Monday because he recorded it sometime last week.
Oh, it's the February 11th one.
Yeah, I
Maybe.
think that's the one.
Yeah,
Okay.
Yeah,
All
I'm
right.
pretty sure he posted it.
Thank you.
Yeah. Good. Any other questions, logistics? If you look on your grade book, the grade book should be pretty accurate. I haven't dropped anything yet. Remember that I will drop 4 of the pre and post lab assignments, and I will drop 1 of the problem sets, but I'm not going to do any of that just yet because it sort of distorts the grade a little bit. About halfway through the semester, probably after the next exam, I'll drop 2 of the pre and post lectures, and then at the end of the semester, I'll drop 2 more in a problem set. Okay, so those things will get dropped. So if you have some zeros in there, that can affect your grade. But other than that, the grade that you see in Canvas should be pretty up to date, and of course, will include your score on exam 1. Okay. Well, it's good to see all of you. Let's get into it here. Equilibrium. So the first thing I want to talk about a little bit is that equilibrium is what happens when you have a chemical reaction that is reversible. And what I mean by that is it can go in 2 directions. Like, for example, this is the hemoglobin oxygen system that allows us to bring oxygen from our lungs and into our muscles and into our brains where that oxygen is being used. And this is hemoglobin, and it combines with oxygen, and it forms hemoglobin bounded to oxygen. So they form a bond. Hemoglobin is a big, complicated protein molecule. So I'm not going to write the formula here because it has thousands of atoms. But it binds oxygen in this equilibrium reaction, which means that the reaction can go forward in the forward direction, but it can also go in the backward direction. Okay. And at some point it reaches equilibrium, which means that there's some of the reactants and some of the products, and they're both present together. All right. So it doesn't completely go to the right, doesn't completely go to the left. It kind of, if you were to look at some hemoglobin with oxygen mixture, right, you'd see some hemoglobin, oxygen, and some bounded oxygen to hemoglobin. All right. Can you guys hear me okay? Yeah. Okay. One other thing about hemoglobin is that, one other thing about equilibrium is that when an equilibrium system is disturbed, right, it tries to counteract that disturbance. So for example, if I have this system at equilibrium, right, which means that they're all 3 existing together, and I were to increase the amount of oxygen, the system would shift to the right to try to consume some of that oxygen back up. Similarly, if I decrease the amount of oxygen, it would shift to the left to replace that oxygen. So this is the way that this works, right? When the blood flows through your lungs, right, what happens? Lung oxygen is high, right? So in the lungs, right, you have a lot of oxygen because you're breathing. So what does it do? It shifts the reaction to the right, and the oxygen gets loaded onto the hemoglobin, right? And then it gets transferred through your bloodstream to your brain and to your muscles. And in those places where oxygen is being used up, right, So in the muscles, right, the oxygen level is lower. So which way does the reaction go? It goes to the left and releases oxygen, right? So it's this equilibrium process where the oxygen level is high, hemoglobin picks up oxygen. Where the oxygen level is low, hemoglobin unloads oxygen, right? So nature has devised this way, right, for the hemoglobin in our blood to get oxygen from our lungs to all the places where we're using it, okay? Now, I tell you a story when my wife was pregnant with my son Kyle, who's now approximately your age. She had they do a blood test on the baby and they can see the blood type that the baby has. And it turns out that he was A positive and she was the blood type that doesn't have any of those proteins, right? So what is that called? Zero negative, I guess, O negative. She was O negative and he was like A positive. And that's not a big deal, but what can happen is if during the birth process, the blood of the baby and the blood of the mom mix, then the mom can actually begin to produce antibodies against that protein. And then if the mom gets pregnant again later, there's a chance that that new developing fetus can be rejected because of that. So there's an easy solution from this. Yeah, I'm talking about the Rh factor. Thank you. There's an easy solution for this. What you do is there's a shot called Rogram, and you take the Rogram and it prevents this from happening, right? But in any case, this whole thing got me to thinking of, well, how does a baby get oxygen, right? Because for some reason, I always thought that the mom's blood would flow into the baby and that's how the baby got oxygen, but that's not the case. Baby has its own blood system. When the mom has the baby inside of her, right, the blood of the mom and the blood of the baby never mix, okay? So how does oxygen get to the baby? Well, the baby has its own hemoglobin, okay? But it has a little bit of a different structure than the maternal hemoglobin. It's called fetal hemoglobin. So HbF we'll call fetal hemoglobin, right? And the same thing happens with fetal hemoglobin. It picks up oxygen, right? And binds oxygen in this equilibrium system. Now, the genius thing about this is that because of a difference in something called the equilibrium constant, okay, the equilibrium constant K, the equilibrium constant is a measure of how far this reaction or any reaction goes towards products, okay? In fact, we'll define it in a minute, but just think of it as a measure of how far this reaction goes to the right, okay? And so there's a K for the maternal hemoglobin, but the K for the fetal hemoglobin is a little bit different, all right? And in fact, it's a little bit bigger, okay? So the K for the fetal hemoglobin is a little bit bigger than the K for the maternal hemoglobin. What does that mean? It's crazy. What that means is that at the same oxygen concentration where the fetal hemoglobin is picking up oxygen because it has a bigger K and it goes further to the right, the maternal hemoglobin is unloading oxygen and going to the left, right? So what happens is the baby's blood and the mom's blood flow very, very close to each other in the placenta, and the mom's hemoglobin hands off oxygen to the baby's hemoglobin. And that's how the baby gets oxygen. And it's all because of difference in the value of equilibrium constants, right? Which is related to a difference in the structure of the hemoglobin for the fetal and the maternal hemoglobin, all right? So that's what we're gonna jump into in this chapter, not necessarily so much about hemoglobin, but the whole idea of equilibrium and how to work with equilibria in chemistry, okay? Awesome. So first, let's define something called dynamic equilibrium. And it's the condition in which the rate of a forward reaction is equal to the rate of a reverse reaction, okay? So in a reversible reaction, the condition in which the rate of the forward reaction equals the rate of the reverse reaction. All right. When those are equal, then we've reached equilibrium. Okay. That's a definition. So let's see what that looks like. So let's say we have this, let's skip this one. Let's say we have this reaction, H2 plus I2 in equilibrium with 2HI. So there's our chemical equation. All right. So we start out with a container, right, with a reaction container, and the reaction container contains hydrogen and iodine, as shown here. All right. And then they begin to react. Well, initially, the hydrogen reacts with the iodine, right? And excuse me for a minute here. I got to fix my display. Sorry about that. The hydrogen and iodine begin to react. So what happens? If we monitor the concentration, right, of the hydrogen and iodine as a function of time, right, we notice that those concentrations go down. Yeah. At the same time, as the reaction begins to occur, right, the concentration of HI, the product, goes up, right? And this part of the curve, of course, is determined by the kinetics of the reaction, right, which we just covered. If for a fast reaction, right, these would go really fast. This would go up really fast. For a slower one, they'd go slower, and so on, okay? But what happens is, as the products begin to build up in concentration, then you start to get the reverse reaction occurring as well, right? And eventually you get to this point in time where equilibrium is established. Remember, at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So imagine a classroom where students are leaving through one door at the same rate that students are coming in another door. Exactly the same rate. What happens to the number of students in the classroom over time at the point where those two rates are equal?
It shouldn't change. Same number of students.
They don't change anymore, right? They stay constant, right? The number of students stays constant. Similarly for the reaction, if you have the forward reaction going at the same rate of the reverse reaction, then the concentrations stay constant. And that's where we've reached dynamic equilibrium, okay? The reaction is still going the forward direction, the reverse direction, but the rates are exactly the same, and therefore the concentrations no longer change, all right? So once we reach dynamic equilibrium, we can specify how much reactant and how much product with something called the equilibrium constant, okay? So let's define the equilibrium constant. For a reaction AA plus BB in equilibrium with CC plus DD, right? Where these are stoichiometric coefficients here, A, B, C, little a, B, C, and D, all right? Then the equilibrium constant K is going to be equal to the concentration of C raised to the C power times the concentration of D raised to the D power divided by the concentration of A raised to the A power, concentration of B raised to the B power, all right? This is where we define the equilibrium constant. It's defined at equilibrium, right? And notice what it specifies. It specifies the ratio of products to reactants, okay? More concisely, it's the product of the product, the products raised to their stoichiometric coefficients, right? Divided by the reactant concentrations raised to their stoichiometric coefficients, right? That's the definition of the equilibrium constant. So what does a big equilibrium constant mean? If an equilibrium constant is really big, what does that tell you about the reaction?
It favors the products.
It favors the products, right? It means that at equilibrium, there's going to be a lot of products and not very many reactants. So for example, this reaction between hydrogen and bromine has a very large equilibrium constant. If we looked at an equilibrium mixture, we'd find a lot of HBr and not very much H2 and Br2, right? In this case, there's only one H2 and one Br2 molecule. Everything else is product, right? That's what a large equilibrium constant means, all right? A small equilibrium constant, so for example, here, this equilibrium constant for this reaction would be the products, NO squared, right? divided by the concentration of the reactants raised to their stoichiometric coefficients, but the coefficients are 1, so it's just N2 to the 1 and O2 to the 1. If that's a small number, right, then what does that tell you?
Favors the reactants.
Correct. The reactants are favored at equilibrium, right? That means that if I looked at an equilibrium mixture, I'd have a lot of reactants, in this case, nitrogen and oxygen, right? And not very many products. Here you only see 2 product molecules, right? Yes, it is exactly the same thing as the seawater salt dissolving and also vapor pressure. We talked so we've already introduced equilibrium a little bit. And this is now we're applying it to a chemical reaction. Okay. All right. Just to make sure you got that, let's try a little poll question here. Let me get that launched. All right. Try answering that question for me. Okay, 5 more seconds. Okay, awesome. Virtually all of you got that. The right answer was B, right? B. Why? Because if equilibrium constant is 2, right, and red is black is the product, right? B are the black circles, right? Then this has 1, 2, 3, 4, 5, 6. So K in this case would be equal to the concentration of B divided by the concentration of A. And how many do we have? We have 6 B's and 3 A's. So that's equal to 2, right? So this is the one that represents K equilibrium equal to 2, right? Does that make sense? Most of you got that, so nice work. Okay, let's move on. Just a couple of quick relationships involving K. These are not too difficult, but if you have a reaction, right, like AABB, right, just a generic reaction, there should only be one arrow there. Sorry, I'm not sure why that other one is there. Then K for the forward reaction, of course, is C to the C, D to the D, and so on, right? Now, what happens if I reverse the reaction? If I write it this way, backwards, right? Then notice what happens for K. Now it's A to the A, B to the B. You just invert it, right? You just invert it. So if you know K for the first forward reaction, K for the reverse reaction would just be what?
1 over K forward.
Right, 1 over K forward, right? And you can see that here. Does that make sense? If you take a reaction, an equation, and multiply the coefficients by some factor, you raise the equilibrium constant to that same factor, right? So let's say we have this reaction, AA plus BB in equilibrium with CC, right? Here's the original equilibrium constant, right? Now, what happens to this if we multiply it by some factor like 2? So now we have 2AA plus 2BB in equilibrium with 2CC, all right? All you got to do is raise K to that same factor, all right? So Ko new is equal to K original raised to the N power, where N is what you multiplied it by. Okay. Taylor.
I just had a question on the graph for the first part. So how you get these K values is where it flatlines.
Correct.
And then at that moment when it flatlines, that's equilibrium.
Correct.
Okay.
Correct.
So like
So it's
experimentally.
the concentrations here that determine K.
Okay. So if you had like an experiment going and then it flatlined, you would know that that's the equilibrium point, and then
Correct.
you could figure, okay.
Yep. Yep.
Okay.
Good.
All right. Thank you.
Yep. Minerva?
Can you go back to the previous slide that had rate forward and rate reverse? No, go forward. Yeah, I think it was this one. Is that everything on there?
Yeah, and that. So if you know K for the forward reaction, K for the reverse reaction is just the inverse of K for the forward reaction.
Okay, great, thank you.
And then this one is just, if you have some reaction, you multiply it by some coefficient, raise K to that same power. Okay? And then the third relationship is, if you can take two equations and add them together to form a third equation, then the equilibrium constant is just the product of the two equations. Of the two Ks, right? So in other words, in this reaction, you can see that I have AA plus goes to BB, and then second reaction, BB goes to CC. And if I know K1 and K2, then I can add these two reactions together, cancel the B's, and I get A goes to C, right? And then I can just get that K nu is equal to just the product of the two Ks. All right, so just three simple things, right? Number one, if you reverse a reaction, you do what to K?
Invert it.
Invert it. If you multiply a reaction by some constant, what do you do to K?
Raise it.
You
Raise it to that
could
constant.
raise it, you square it, I guess.
Exactly. Raise it to whatever the constant is that you multiplied the equation by. And then thirdly, if you have two reactions that sum to an overall reaction, the equilibrium constant for the overall reaction is just the product of the inner equilibrium constants for the individual reactions. Okay? All right, here's a quick question for you. Okay, 5 more seconds. All right, very good. The correct answer was D, and most of you got that. So nice work. Okay. It's basically, this is just A, B, and C are a summary of what we just covered, right? Perfect. All right, now when you have a gas, when you have a gaseous equilibrium, like this one where they're all gases, you have the option of expressing the equilibrium constant in two different ways. You could either express it as Kc, so we'll put a small c down here, which is the way we just defined it. Concentration of C raised to the C power, D to the D power, and so on. But if they're gases, you have the option of expressing the equilibrium constant, not in terms of concentrations, but in terms of partial pressures, okay? Concentrations are always gonna be in moles per liter. Partial pressures are always gonna be in atmospheres, ATMs, okay? And so notice in this case, this is the partial pressure of C raised to the C power, partial pressure of D raised to the D power, partial pressure of A raised to the A power, partial pressure of B raised to the B power, right? So it's the same exact definition, except that you have partial pressures instead of concentrations, all right? And for gases, for reactions like this, in which everything is a gas, the equilibrium constant might be expressed this way or this way. Either way is fine, but they don't necessarily have the same value, all right? The relationship between them is Kp is equal to Kc times RT to the delta N, where Kp is the equilibrium constant with respect to partial pressure, Kc is the equilibrium constant with respect to concentration, R is the ideal gas constant, right? 0.08206 liter atmosphere moles Kelvin. T is the temperature in Kelvin. And this delta N, all right, this delta N is equal to C plus D minus A plus B. So what is this delta N? It represents the difference in the stoichiometric coefficients, right, between the products and the reactants, right? It's the sum of the stoichiometric coefficients for the products minus the sum for the reactants, okay? And that's a relationship between these two. So let's just do a quick example here. So you have this reaction, and you know Kp, right? And you want to find Kc. So if we use this equation and we solve it for Kc, right? Kc is going to be equal to Kp times RT to the delta N, okay? And we're given Kp, so Kp is 1.9 times 10 to the third, divided by RT, 0.08206 liter atmosphere mole Kelvin, times the temperature, 298 Kelvin. And this is all raised to the delta N. Now, what's delta N for this reaction? Well, delta N is equal to the sum of the coefficients for the product, so that's 2, minus the sum of the coefficients for the reactants, which is 3, right? So delta N is equal to minus 1. Okay, so this is raised, this denominator here is raised to the minus 1. And if you multiply that out, you'll get 4.6 times 10 to the fourth. Does that make
Wait, why
sense?
did you put for the Kc? Why did you do Kc equals Kp over the RT?
If I take this equation and I solve it for Kc, right? Kc is
Oh,
equal to
yeah, yeah.
Kp divided by RT to the delta N.
Okay, got it.
Got it? Ryland.
Oh, that was from a minute ago. I was just curious, what makes a reaction reversible? Are they all reversible to some more greater or lesser degree, or are only some reactions reversible?
Yeah, so it's a great question. What makes a reaction? So really, the real crux of your question is, what makes a reaction go at all, right? What makes some reactions go more than others? So some reactions, so to answer your question, in theory, all reactions are reversible, but some go so far to the right that you don't have to worry. You really don't have to worry. The equilibrium constant is huge, right? And so you don't really have to worry about there being some reactants left over at the end. Some reactions go so far to the left that you don't have to worry about those at all either. They basically don't go, okay? But then there's a lot of reactions that kind of go halfway or part way, right? And those are the ones that where we worry about K. Now, why some reactions go way to the right and some don't is related to thermodynamics. And that's related to entropy. And that's going to be the topic that we'll get to in a couple more weeks. Okay. So we want to understand, well, why are some, right now we're just saying, hey, look, K tells you how far a reaction goes, but we're not really we're not really investigating why that's the case. We're just going to accept it. We're just say, okay, K tells us how far a reaction goes. Later on, we'll come back and we'll ask the question, why? Why do some reactions have bigger Ks than others? Right? So we'll get to that question. Does that answer your question?
Yeah.
Okay.
thank you.
Sorry, this should have said 298 Kelvin. Okay, or 25 degrees Celsius. All right. Let's see, Abe.
Nah, you answered my question. I was just gonna
Okay.
ask if we just assume it's 298 for like.
Yeah, it wasn't on here, but we're just assuming 298.
No, you're good.
Okay, let's do another one here. How about this one? H2 plus Br2 goes to 2HBr. You're given Kc is equal to 52, right? And you want to find Kp. Well, Kp is equal to Kc times RT to the delta N. But what is delta N for this reaction?
0.
Yeah, delta N is 0, right? Because 2 minus 1 plus 1 is 0, right? So delta N is 0. Well, if delta N is 0, then what's the case? RT to the 0 is what? What happens when you raise any number to the 0 power?
1.
1, right? So this becomes 1. So Kp is equal to Kc. So in this case, they give you Kc and Kp has exactly the same value, right? So in situations where the sum of the coefficients for the products and the reactants are exactly the same, Kp and Kc are equal. Okay? All right, let's
I have
have
a question.
question.
Yeah. How exactly did you get to 0?
Oh, okay.
Because they equal each other? Is that why?
No. Because remember what this delta N is. It's the sum of the
Yeah, you raise it to 2.
No. It's the sum of the coefficients for the products minus the sum of the coefficients for the reactants, right? So it's 2 minus, so delta N here is equal to 2, which is this number, right?
Mhm.
Minus 1 plus 1,
Okay.
right? So that's 0.
Yeah, got it. Thank you.
Right. Okay, let's have you try one. Okay, another 10 seconds. All right, I'm going to stop it there. And most of you got that right. The correct answer was E. So nice work. In this case, delta N, right, is equal to what? 3 plus 1 minus 1 plus 1, right? So it's 4 minus 2. So that's equal to 2, right? So you got Kc is equal to Kp times RT to the delta, divided by RT to the delta N. You put in your Kp up here, RT, and you raise it to the second power, and you get 1.29 times 10 to the 22. All right, I saw some questions about units here. And you know, from the beginning, I've been really encouraging you to always write down your units for everything, right? Because units help determine correctness. For equilibrium constants, it doesn't work out that way, all right? And that's because equilibrium constants really have a more complicated definition that really we don't have to worry about for this class, all right? If you want to know, it's in the book. It's basically that the concentrations are always defined with regard to some reference concentration. So for solutions, it's 1 molar, and for gases, it's 1 atmosphere. So the units actually cancel out in the definition, but you don't have to worry about that. All you have to worry about is that whenever you see Kc, you should always use units of molar. And whenever you see Kp, you should always use units of atmospheres. Okay? Those are the only units that we'll ever use for Kp and Kc. All right? All right. And as you can see, when you work out a problem like this, the units don't really work out. Okay? And so that's going to be the case every time we use equilibrium constants. All right. Now, so we have this nice definition for K, right? Right here. Right? Concentration of products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients. We have a nice definition for Kp, right? Which I don't have. It was just on a previous slide, but Kp is the same thing except instead of concentrations, we use partial pressures, right? But now, what happens when you have an equilibria that has, let's say, some gases and something like a solid? Okay, so right, you might think that this, for example, if we were to write the equilibrium constant for this reaction, let's say Kc, that it would be the concentration of CO2 times the concentration of carbon divided by the concentration of CO squared. You might think that, but in fact, the carbon is left out of the equilibrium expression. Why is that? Because the carbon concentration is determined by the density of carbon, right? So if the density of carbon is whatever it is, 5 grams per centimeter cubed, that determines the concentration. And as long as I have some carbon present in the solid form, its concentration doesn't change, right? It's determined by the density. It doesn't be, because gases, right? If I have more volume, the concentration goes down. If I have less volume, the concentration goes up, right? And so on. But for a solid, can't change the concentration. And the same is true for a liquid. The liquid is determined by its density, and you can't change its density, and you can't change its concentration. Okay, so solids and liquids are omitted from Kc and Kp, right? They do not go into the equilibrium expression, right? So in this case, Kc would be equal to the concentration of CO2 over the concentration of CO squared. Kp would be equal to the partial pressure of CO2 divided by the partial pressure of carbon monoxide squared, right? But notice that there's no carbon solid in the equilibrium expressions, okay? So solids and liquids are left out, yeah? Questions? Yes, I mean a pure solid or a pure liquid, correct. Minerva?
Can you go over how to calculate delta N again?
Yeah, so delta N, let's just see, what would delta N be for this equation right here? It'd be 1 plus 1. Actually, not in this case, this wouldn't be a 1. So it would just be 1 because we wouldn't include the solid. 1 minus 2, so it'd be negative 1. So you just sum the coefficients for the products and then subtract the coefficients, the sum of the coefficients of the reactants. Okay?
And Tro, for that last one, the bottom, the numerator, it's squared because there's 2 of the COs.
Correct.
Okay.
Right there. Yep. Good. Delta N is only for, yes, the gases. Correct. Okay. Now, let's move on to calculating equilibrium constants. So the important thing to realize about an equilibrium constant is that no matter where you start a reaction, it's always going to go to a place where the concentrations, when you plug them into the equilibrium expression, right, are going to equal K. So let's say, for example, here's a reaction, hydrogen and iodine to form 2HI. Okay, the equilibrium constant for this reaction is 50. So what does that mean? That means if I start out with, let's say, 0.5 molar H2 and 0.5 molar HI initial, I let the reaction go. Here are the concentrations at equilibrium. When I plug those concentrations into the expression for the equilibrium constant, guess what I get? 50. Okay? If I start with no reactants and only products, then this reaction is going to go to the left, right? Some of the HI is going to form H2 and I2, so that when it reaches equilibrium, I get these concentrations right here. And if I plug those into the expression for K, guess what? I get 50 again, right? No matter where I start over here with the initial conditions, the reaction is going to go in such a direction so that when equilibrium is reached, the concentration of HI squared divided by the concentration of H2 times concentration of I2 is always going to be 50 for this reaction, right? Here, if I start out with all 3 of them together, all mixed together, 0.5 molar of each, let it get to equilibrium. I get these concentrations at equilibrium, plug them into the equilibrium constant expression, 50. Right? It doesn't matter where I start. The reaction is going to go to a place where when I plug them into here, I get 50. That's what it means to have an equilibrium constant of 50. Does that make sense? Okay, so let's do a simple example, and then we'll look at a little more complicated one. Let's suppose I have a reaction A gas in equilibrium with 2B gas. Okay, and let's say that the concentration of A initial concentration of A is equal to 1.00 molar, right? And the initial concentration of B is equal to 0.00 molar. In other words, I have a container that just contains reactants, no products. All right. And then at equilibrium, I have that the concentration of A, I measure that again, and it's 0.75 molar. So it's fallen from 1 molar to 0.75 molar. And I want to find Kc. All right. I want to find Kc. So remember what Kc is. Let's just write the equilibrium expression for that. Kc is equal to the concentration of B squared, concentration of A squared. But these concentrations, are they initial concentrations?
At equilibrium.
Only at equilibrium, right? These concentrations have to be concentrations at equilibrium. All right. So notice in this case, they give us initial concentration of A and initial concentration of B, but that's not what goes into here. What I need are the equilibrium concentrations, and they only gave me the equilibrium concentration of A, right? But I can use stoichiometry to get the equilibrium concentration of B as well, and then I can plug it into here and get the value of Kc. The easiest way to do that is to create something called an ICE table. So an ICE table, you basically use the reaction to set up columns for each of the reactants and products, okay? And then you have 3 rows. You have a row for initial, a row for change, and a row for equilibrium. So boom, 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 boom. Okay. Do it like that. So what's my initial concentration of A for this problem?
1.0 molarity or 0.0
Right.
molarity.
0.0. Initial concentration of B?
0.00.
0, right? So no B, okay? Now, when it went to equilibrium, it went from 1 molar to, at equilibrium, A went to 0.75 molar, right? So if this went from 1 to 0.75, what was the change?
0.25.
Negative 0.25, right? Negative 0.25. Now, if this went down by 0.25, right? And I have a coefficient of 2 here. What happened to the concentration of B? What was the change in the concentration of B?
Positive 0.25.
Positive 0.25?
No, times 2.
Has to be times 2, right?
Yeah.
So you were on the right track there with the positive 0.25, but because of this coefficient, for every mole of this that reacts, I get 2 moles of that. So if 0.25 moles of this react, I get
0.5.
0.5. So this is going to be plus 0.5, right? And then at equilibrium, I just sum these, right? So this minus that gives me that. This plus that gives me that. Okay. So now these represent my equilibrium concentrations. All right. I call these tables ICE tables because they're after initial, change, and equilibrium. Okay. And we're going to be using these tables quite a bit in the next couple of weeks. Okay. So now I have my equilibrium concentration, so I can find K, right? Kc is going to be equal to what? The concentration of B, which is 0.50 squared, divided by the concentration of A, which is 0.75. Right? So that equals 0.33. Does that make sense? Let's look at a little bit more complicated problem here. And I'm just going to use this example from the book. So you have this reaction, all right? A reaction mixture contains 0.5 molar CO and H2 equal to 1 molar. All right. And then at equilibrium, the CO concentration is found to be 0.15 molar. And they wanted you to find the equilibrium constant, right? So we can set up a very similar thing. We can set up the ICE table, CO plus 2H2. Again, use the balance reaction to set up your columns, right? And then you're going to do ICE, initial, change, equilibrium, right? That'll set up your rows, right? And you're given that the CO concentration initially is 0.5, so you just fill this in, right? And H2 is 1.0, right? And at equilibrium, you find that this is 0.15, right? So this went down by how much? Minus what?
0.35.
Went down by minus 0.35, right? That went down by minus 0.35. So now, according to the stoichiometry, right? If this went down by minus 0.35, then hydrogen, which is also a reactant, had to go down by how much?
0.70.
Minus 0.70, correct, right? It had to go down by twice as much. Why? Because of that 2 right here, right? There's a 2 right there, and so you have to have minus 2 times 0.035. Does that make sense? And then if this went down by 0.35, right? Then what about CH3OH? What's that change?
Would it also be negative 0.35?
It would be 0.35, but it'd be positive, right? Because this is a reactant and that's a product. So the reactant and the coefficients here are 1 and 1, right? So if this went down by 0.35 and this went up by 0.35, right? So then we just sum the table, right? So this is 1 minus 0.7, which is 0.30, and this is 0.35. So now we have our equilibrium concentrations.
That would only change if there was a different coefficient, right?
Correct.
Okay, cool. Perfect.
Correct. So you just have to take into account these coefficients every time,
Okay, perfect. Thank you.
right? This 2 here, this is 0.7 because there's a 2 there, right? All
So
right.
is the initial for the product always going to be 0 because the reaction hasn't happened yet?
Not necessarily. It could be that a reaction mixture has some of the product in it already, in which case you would just put the concentration there and you just add or subtract just like normal. So it could happen. All right. So then we're going to write out the expression for K. This is asking us to find, this is all in molarity, right? So we're going to be finding Kc. So what's the expression for Kc? The concentration of CH3OH, right? The product divided by the concentration of
The reactants.
the reactants, right? CO, each raised to the stoichiometric coefficient. CO is 1, and H2 should be raised to what power?
2.
2. Right? Does that make sense? So then we just plug these things in, right? 0.35 divided by 0.15 divided by 0.30 squared, right? The squared is there because of that has to be squared. All right. And so you plug that all in, right? And you get that that's equal to 26. Does that make sense? Okay. Let's have you try one. Okay, about 15 more seconds. Okay, I'm going to end it there. And the correct answer was D. And most of you got that. So very, very good. Basically, what you're going to do is you have this reaction, right? And you're given initial mixture. Initial is 1.0 molar and 0, right? At equilibrium, the concentration of B is 0.25, right? So you know that this was positive 0.25, right? So if that went up by 0.25, this had to go down by how much?
0.5.
Yeah, minus 0.5, right? So this is 0.50 when you sum it. This is 0.25. You plug into the expression for K, which is B divided by the concentration of A squared. So that's 0.25 divided by 0.50 squared, which is equal to 1. Okay, nice work. All right, good. Any questions? Is this making sense? Okay, delta N, what would be delta N for this reaction?
Is it 1?
It'd be this coefficient, which is 1, minus this coefficient, which is 2, which would be minus 1. Right?
So then why is it 2 when you write it B over A?
Squared. Okay, this delta N only applies,
Yeah, yes.
this delta N only applies to this equation. Right? That's only when you're figuring out the relationship between Kp and Kc. The definition of K doesn't have any delta N in it. The definition of K is just the concentrations of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. There's no delta N in the definition of K. That delta N only comes in the relationship between Kp and Kc.
Okay.
Does that make sense?
Yeah.
Okay, great. Okay, the reaction quotient. So now we're going to define something that's going to look identical to the way we define K, but it's not going to be K. It's going to be Q. All right? So bear with me here for a moment. The reaction quotient for a reaction AA plus BB goes to CC plus DD. QC is equal to the concentration of C raised to the C power, concentration of D raised to the D power, concentration of A raised to the A power, concentration of B raised to the B power. And then QP, which is with respect to partial pressure, is the partial pressure of C raised to the C power, partial pressure of D raised to the D power, partial pressure of A raised to the A power, partial pressure of B raised to the B power. Now you're going to tell me, wait a minute, this looks just like the definition of K, right? And it does, but there's one important difference. K is defined only at equilibrium. Q can be at any other place in the reaction progress, okay? Q can be at any point in reaction progress, right? So in other words, let's go back to our very first slide that we saw for equilibria. This one. So K is only defined here, right? K is only defined once you reach this stability place, but Q can be defined anywhere, right? So for example, for this reaction, Q is equal to the concentration of HI squared divided by the concentration of H2 times the concentration of I2, right? Now, what is Q at time equals 0? from this graph? Based on this graph, what is Q at time equals 0?
0.
0, right? Q is equal to 0 here at the beginning. And then what happens to Q as the reaction proceeds? So what would Q be like right around here? It'd probably be like around maybe 1, right? And then it would get bigger and bigger and bigger until it reached what? The value of K, okay? The value of K. So that's the difference between Q and K. K is only defined at equilibrium. Q can be defined anywhere along the reaction process. So I don't like that figure. Let's look at this one and see if we can understand this. So let's suppose we have the reaction A in equilibrium with B. Okay. And we know that K is equal to 1.45, right? And let's say that A is equal to 0.33 molar and B is equal to 0.66 molar. And the question is, in which direction does the reaction proceed? Well, first question we might want to ask is the reaction at equilibrium or not? Well, let's calculate Q. Q is the concentration of B over the concentration of A is equal to 0.66 divided by 0.33, which is equal to 2. So is the reaction at equilibrium?
No.
No. If it was at equilibrium, what would Q be? It would equal K.
About 1.45.
It would equal 1.45, right? If it was at equilibrium. But it's not at equilibrium. In fact, what does it have too much of? Too much product or too much reactant?
Too much product.
Too much product, right? So which way will this reaction go?
Left.
Left. Okay. We can generalize this as follows. If Q is greater than K, like it was in this case, then reaction goes left towards the reactants. Let's suppose we had found Q was only equal to 1. Right? Let's say Q was only equal to 1, then Q would be less than K. And which way would the reaction go under those circumstances?
Going to the right.
Right.
Right. If Q is less than K, reaction goes right. And if Q is equal to K, what do we know?
Equilibrium.
Right, exactly. Reaction is at equilibrium and it won't go in either direction. Does that make sense? Taylor? Question?
Yeah, I understand the Q and K, but like if you were doing this like real life or like in the real world, like when would you not know your Q already? Like, does that make sense? Like what would be the point of finding Q?
Sure. Let's say, I'll just think of some off the top of my head here. Let's say you're carrying out a reaction. You know that the equilibrium constant is 100, right? Let's just say. And so you're carrying out the reaction and you want to try to get as much product as possible, right? So you want to know, okay, where am I in the reaction? Have I gotten to 100? So you measure the concentrations of the reactants and products or whatever, and you find that Q is only equal to 50, right? So what do you know? Oh, I haven't reached equilibrium yet. I should let this reaction go further because I'm going to get more product if I just wait a little longer. That's one example off the top of my head.
Okay. So it's kind of measure like how far the reaction has gone.
Correct.
Kind of over time. Okay.
Correct.
Like incomplete. Basically.
Correct. If you start with all reactants and no products, right? Q is always going to be what?
No reactant.
All reactants and no products. So Q will be 0, right?
Yeah.
Q will be 0 if there's no products, right? So if this is 0, then 0 over whatever this is 0. So Q, for a reaction in which you start with only reactants, Q is equal to 0. And it's going to go towards products until Q equals K. Now, if you start with all products, let's say you have a reaction in which you start with all products. all B and no A, then Q is equal to what in that case?
Infinity?
Infinity. Infinity, right? Since we're chemists, we can divide by 0 and call that infinity. Mathematicians don't like that, but chemists do that all the time. So we can just say it's infinity. And since it's infinity, Q is greater than K, so reaction is going to go to the left, right? It's going to go to the left until you get enough reactants in the mixture, right? So that Q is equal to K. So Q is always going to revert towards K, right? If Q is less than K, then you know it's going to go to the right. If Q is greater than K, you know it's going to go to the left. If Q is equal to K, you're at equilibrium.
Okay. So you can know K before you know Q. Like, I mean.
Sure. Yeah. Yeah.
It's kind of weird to me.
K is fixed for a given reaction at a given temperature. Right?
Ah,
K never changes for a given reaction at a given temperature. So if you have some reaction, like, you know,
so it's standardized.
so for example, here, this reaction, right, at this temperature has a K of 26. And as long as you carry it out at that temperature, K is going to be 26, no matter what. Q can be anything, right? Like what's Q here initially? Well, it's 0 divided by this square divided by that. So Q is 0 initially, right? But eventually Q is always going to be equal to K when it reaches equilibrium.
Okay.
So one way to think of Q is a measure of where you are relative to equilibrium.
Okay.
Right? Q kind of tells you, hey, where are you relative to equilibrium? Do you have too many products and things are going to go towards reactants? Or do you have too many reactants and things are going to go towards products? Or are you at equilibrium, in which case Q equals Q.
Okay. So since K is a case by case basis, and you can know what K is, Q just gives you a reference point of where you are.
Correct.
Okay. All right. I was confused on that. I was like, how do you know what K is? And I was like, okay, but you can standardize it. Okay.
Correct. Yeah.
All right. Thank you.
Okay, so let's try a question.
Hey, Professor.
Yeah.
At what point does the reaction decide to switch directions? Like, is it sort of like a spring? Like it reaches like a certain point where it's like, time to turn back, or?
No. Let me finish this question and I'll answer your question, okay?
Okay.
Oh, very good. Most of you are getting this. Awesome. You guys are on it today. Okay, about 5 or 10 more seconds. All right, so the right answer was A, and look at that. Almost all of you got it. Very, very nice. For those of you that didn't get it, K, right, the expression for Q is concentration of B squared divided by the concentration of A, right? So this is 2 squared over 1, which is equal to 4. So Q is equal to 4. You compare Q to K. Q is greater than K, right? So the reaction is going to go to the left, right? Reaction goes left. Okay, so how does a reaction decide where, well, it doesn't really, I guess it doesn't decide. It just always is going to go in the direction of K. So I think the easiest one to see is going back to this one. Right, if I have a graph of the reactance as a function of time, right? What's going to happen here, like for example, here at the beginning, right? Q is equal to 0, right? Because Q for this reaction would be equal to the concentration of HI squared divided by the concentration of H2 and the concentration of I2, right? So initially here at time 0, right? That's equal to 0 over what? Let's say the top of that graph is 1, right? So it would be 1.0 times 0.8, let's say, right? And so that's 0, right? So Q is equal to 0, so it's going to go to the right. And so it'll keep going to the right, and it'll asymptotically approach K, right? And then at some point it will be K, and it won't most reactions don't overshoot. In other words, they don't go too far and then come back. There are some reactions that do that. They're called oscillating chemical reactions. They'll oscillate back and forth, and they're kind of cool, but they're rare. Okay. Typically, it just goes down and it approaches K. If you were to start with all HI and no H2 and I2, then what you would see is that the HI would go down and the H2 and I2 would go up until again, you reach equilibrium asymptotically. Does that make sense? Okay, very good. Let's see, where were we? Good. Okay. I think that's all for today. I think I'll end it there. Next time, what we're going to do is a kind of problem that we're going to do a lot again in the next couple of weeks. And that's if you're given the initial concentrations for a reaction, how can you find the equilibrium concentrations? So far, the kinds of problems we've been doing, I've been giving you the equilibrium, the initial concentrations, and some equilibrium concentrations, then asking you to find K, right? But now we want to switch to, okay, I'm going to give you K, I'm going to give you the initial concentrations, and I want you to find the equilibrium concentrations. That's where we're going next time, okay? Thanks a lot. I'll stick around for questions, but if you don't have any questions, you're free to go and enjoy the rest of this beautiful sunny day in Santa Barbara. Be grateful. The rest of the country is covered in snow and ice.
Snow's fun though, right?
What's that? Oh, my poor brother lives in Oregon, and they had a big ice storm, and he's out of power for 2 or 3 weeks.
Oh man.
No running power, no electricity, none of that. Can you believe it?
That sucks.
Yeah, pretty bad.
Insane. I like how we think snow is this magical thing, and then it like totally destroys your life, you know?
Snow is fun when you can like go up to it and play. Like I actually went up to Mammoth this weekend and did a little snowboarding, and it was beautiful, right? But then you come home and it's sunny and warm. Living in it, especially if you live in a city where it shuts down so much. I have I had a meeting yesterday with one of my colleagues from Pearson who's in Chicago, and their city's just been shut down for a couple of days because there's so much snow. It's just all over the country. We're really lucky here.
And we get so excited when there's like half an inch of snow up by La Cumbre Peak.
Yeah, right.
All right, thank you, Professor. Have a great rest of your week.
Thanks, Isabella. Excuse me. All right, let's see. Thank you. All right, I see some questions here. Let's start with Ryland.
I just had a general question. How far into chapter 16 should I be read in order to be caught up with the material for this week's problem set?
Yeah. On the excuse me, on the Canvas homepage, there's a schedule, and
Okay,
looks
cool.
something like
Okay.
this. Sorry, I
Mhm.
can't get in the right place. Anyway, it looks something like this, and I've been sticking pretty much dead on to that schedule, and so you can always look on there. But just to answer your question, let's see. Today's the 22nd. We're talking about no, today is the 17th. Sorry. We're talking about chemical equilibrium. Next, we will finish chemical equilibrium on Monday.
Mhm.
So you basically, we've covered all this part of the chapter, right, through all these topics, and we still have these 2 topics to cover. But these are the longest and hardest topics of the chapter. So basically, in order to be ready for the problem set, you should read through section 16.5. This is section 16.6 here, and that will not be on the problem set.
Cool.
16.5 will be. Yep. Michael. Michael Quinn? Question? Did you have a question? Oh, I think he's gone.
Hello?
Taylor. Oh, Michael, you there?
Oh, sorry, my headset got unplugged.
Oh, no worries.
I don't have a front-facing camera today. My laptop broke and it is been returned. But I have a question on the homework problem, exercise 16.39.
Okay, let me bring that up here. Give me a minute. Sorry, it takes forever to load. Let's see, we're talking about this problem set, right? 16.39. Right. So you have 2NO plus Br2 in equilibrium with 2NOBr, right? And you're given Kp is equal to 28.4, right? And so you know the equilibrium expression, Kp is equal to the concentration of NOBr squared divided by NO squared divided by Br2, right? And they're giving you the concentration of, they're giving you the partial pressure of NO, 118. They're giving you the partial pressure of this, 129, right? And you got to find the partial pressure of NOBr, right? And you're given Kp. So Kp is equal to 28.4, right? So you basically just solve that equation for NOBr concentration, and then you're done. Does that make sense? Michael? Oh, I know that. I know. Perhaps the problem you're having is that these have to be, these are given in torr and they have to be in atmospheres, right? So you divide each by 760 torr to get it in atmosphere. Maybe that's a problem you're having. that answer your question, Michael? Can't hear you. Okay, let's move on. Taylor.
Yeah, mine was on the pre-lecture for today.
Yeah. Let me go. Let me pull that up real quick.
Okay.
Oh, that's the wrong one. Next week's. Oh no, that's right. That's the right one. So which one of these?
It's part 2. And then section C. So the last one on the page.
I got 0 on this question too, part 3, the last part.
Yeah.
All right. So you have a 10-liter vessel, or at least that's the number I got. You probably might have a different number, but you're given the amounts of each of these reactants. So you got 4.40 grams of CO2, 2.00 grams of carbon solid, 7.05 grams of CO, right? And you get this reaction, CO2 gas plus carbon solid in equilibrium with 2CO, right? And they're giving you Kc is equal to 5.87 times 10 to the minus 2. And they're asking you in which direction does the reaction proceed. So what you got to do is calculate Q, right? Now remember the Q for this reaction is going to be equal to the concentration of CO squared divided by the concentration of CO2, right? Carbon is a solid, so it does not go into the expression.
Yeah.
Okay.
But can you do molarity, or do you have to do a partial pressure?
You have in this case, they're giving you Kc, so you have to do molarity.
Oh, so that's how you know.
Right.
I was trying to do the pressure.
Right.
I
So they
think.
give you Kc. If you can use partial pressures if you have Kp, and I suppose you could convert this over to Kp and work that way, but why do all that extra work?
Yeah. Okay.
So you convert that to moles, you convert that to moles, right? You divide each by the volume, and that'll give you your concentrations that you plug into here.
Okay. So if you're given Kc, you work in moles.
Correct.
Or molarity, excuse me.
Correct.
And then if you're given Kp, you work in partial pressures.
Correct.
Basically. Okay.
Yep.
Okay. I think that's where I messed up, because I was trying to do partial pressure and I think I messed up